the average value of a function, and where I kind of went with that was it was really hard to find the average value of a function, right? Without calculus, probably could say it's impossible, simply because how many y values are there on any one interval, and the whole add them up and divide by the number of numbers thing kind of falls apart when the number of things you got to add up is an infinite number of them, right? Simply can't do it. So then kind of the extension of this is the mean value theorem for integrals. And so with the mean value theorem for integrals, let me just, I guess maybe I'll run through this here real quick, and then maybe we'll look at this from a slightly different approach than maybe you've seen in the past. So there is one condition for this, and the condition is f must be continuous. If f is not continuous or we don't know about it, then we really can't apply this. And then this is it right here. If you notice on the left-hand side, this might be a good review. Does anybody recognize what is in that left box? That's average value. Yep, so that's average value of f on that interval from a to b of f. There we go. And that is set equal to f of c. So in other words, you could say somewhere the instantaneous height is equal to the average height. Somewhere on the interval, you're going to actually hit your average as long as the function is continuous. So I could draw a picture of this, and that might be a worthwhile thing to see here. So if I've got the y and I've got the x, like so, and I've got this interval from a to b, and I got this function graphed here, say goes from here to there, something like that. I drew a nice continuous function there. Wouldn't the average have to fall within this orange range that I've just created? I'll highlight it. So I get this nice orange range. And if you know how averages work, a measure of central tendency, doesn't the average have to show up somewhere in that orange shaded area? So let's say that the average was, I don't know, right about there. Then you see how the graph, the continuous graph, actually has a y value that is the same as the average value. It's that intersection point, right? Okay. That's kind of the basic premise here. You guys, this is maybe a good review. I think this is probably worth doing here. Do you guys, obviously you recognize that phrase, the mean value theorem. What's the basic premise of the mean value theorem for derivatives? This is definitely a review. We did this last chapter. Okay, so that's a condition, absolutely. So in order for the mean value theorem for derivatives to apply, then f has to be differentiable and continuous, true. But what's the hypothesis of the mean value theorem for derivatives? Oh my goodness.
Can you say it again?
What is the hypothesis? Like, what's kind of the core idea of the mean value theorem for derivatives?
There must equal instantaneous rate or the average rate.
Something about instantaneous rates and average rates, I agree. Brandon?
Is it if a function is continuous and differentiable, and somewhere on an interval that average value must be the derivative?
You're really close now. Okay, you started off so awesome, and then you were half right on the last part. Yeah, the average slope equals the derivative. Yeah, so that's exactly right. So that, if we were to write that out, then I'll just put this over here. I'll put MVT for derivatives. Then that would be f prime of c is equal to f of b minus f of a all over b minus a, right? That's assuming that f is continuous and differentiable on this interval from a to b. You got to see some similarities here, right? Yeah? Do you see the similarities? Wonder if it could be manipulated into being the same. Any ideas?
Take the derivative.
Take the derivative of what?
Oh, you want to be over. You just take the derivative of c and then you take the derivative of f of x.
Well,
Then
what's hard about that is that this over here, I'm highlighting there in the orange box, that's actually a constant, right? Isn't the integral from a to b of f of x, so you can just end up being some number?
if you take the derivative of the integral, then it's
Not a definite integral. So a definite integral where both the limits are numerical, like the a and the b, that's just a number. So if I differentiate the left side, I can tell you right now the answer will be 0. So, yeah, I don't know. What do you think, Jeff?
What the integral from a to b of f of x equals to f of b minus f of a.
Yeah, so it would actually be, so the antiderivative of little f is not little f. It would be like capital F. I don't know if you guys are used to that kind of notation. So it'd be a little bit different. But let's explore that a little bit. So if we did that, if we said, hey, you know, this is really 1 over b minus a times capital F of b minus capital F of a, and that's equal to f of c, right? This is actually the same relationship. When you look at this, what's the relationship between capital F and little f? Isn't little f just the derivative of capital F? And if you look at the MVT for derivatives the way we normally see it, isn't the relationship between little f and little f prime the same as the relationship between capital F and lowercase f? It's the same thing. And all we did was sort of take Jeff's suggestion and actually find an antiderivative. That's all we really had to do, right? So it's the exact same relationship. The requirement, the condition is just a little bit different. You don't need to have it be differentiable for the MVT for integrals to work, simply because it's okay to have sharp points in there and still have an average and hit that average. For derivatives, a little bit different, of course. I just want to show you, it's the same thing. It's the same relationship, just kind of manipulated a little bit to reflect something, a different goal of average value versus average slope. It's really all it is. Anyways, that was all just extra credit. You don't really have to know that, but anyways, so let's go ahead and use this idea of the mean value theorem for integrals, and it is right here. So it says, find the average value of the function on the interval. So that's something you did last time, and we hopefully can do that again here this morning, get a little review in. And we're supposed to also find all the values of x on that interval where the function actually equals its average value. So this is more of the MVT for integrals. So if you guys would, at least, see if we can get to a place where we have found the average value of the function on the interval. Ready, set, go. You could say something like, because f of x is continuous, and then once you've said that, you can just kind of roll with this and you can apply this mean value theorem. How do we know that this function is continuous? Polynomial, it's cubic, yeah, exactly. So I'd start off with maybe something like this. F of x equals 1 over 2 minus negative 1 times the integral from negative 1 to 2 of 4x cubed minus 3x squared. What I've done there is I have set up an important relationship between the average value, which is on the right side of my equation, and the y value of the function, which is on the left side of my equation. And because f of x is continuous, I know for sure that there will be at least one x value where the y value of the function equals the y value of the average value. Sir?
why did you set it equal to f?
Well, that's what I was just saying. So like the mean value theorem for integrals says that as long as the function, in this case f of x, is continuous, then if you find the average value, and which that's what this is right here, it's the average value, then somewhere on the interval, that average value will equal the y value of the function. So I'm just kind of setting it up early. You could set it up late if you wanted to. I just decided I'd do it early. There'd be nothing wrong with doing it late. Okay, so f of x then equals, and you could put like f of c there, just to indicate that c is going to be some number between a and b. I hardly think that that's necessary. Equals 1/3. This would be, as you guys probably noted, x to the 4th minus x cubed, evaluated from negative 1 to 2. And as you process this, you end up with f of x equals 1/3. and it would be 2 to the fourth is 16 minus 2 cubed is 8. And then it would be minus, I guess it would be 1 plus 1, wouldn't it? So 2 there. And then look at that. 1/3 of 6 is 2. So I still have this relationship going. I've said that, hey, the y value of the function has to equal the average value of the function somewhere on the interval. I've gotten down to this f of x equals 2. So maybe this is where I fill in what f of x actually is and try to solve it. 4x cubed minus 3x squared is equal to 2. And this might be where you have to break out the calculator, right? Up to this point, it's been pretty easy without. This, not going to go as well. So you find the intersection point, you find the 0, however you want to rearrange this. What did you guys get? Was there just one value?
Yeah,
There was just one. What'd you get?
1.137.
You guys agree with his value? 1.137? Okay. And it is in the interval, right? So if you would have told me 6.4, don't we have a fundamental issue here? It's got to be within the interval from -1 to 2, right? So, yeah, Josiah.
Would this be a problem, like on a quiz, you would do like no calculator and then you use method?
So if it was on a quiz, would it be no calculator and then
Use Newton's method to find?
that would be an awesome combinations of things, yes. Be tough, it'd be tough to expect you to, it'd have to be carefully designed so that it wouldn't take you like 20 minutes, right? Anybody else? But you have definitely found a use for Newton's method, right? Absolutely. Okay, let's flip over. So the next part here was part of the intro video. Is a continuation of the fundamental theorem of calculus, and definitely going to be used right here, right now. So if you would, maybe you remember this. If you guys could, please take a look at number 2. Number 2, if you know the fundamental theorem of calculus, part 2, FTC 2, if you know that trick, question like number 2 should hopefully go really well. If you don't know the FTC 2 concept trick, you're going to get really hopelessly stuck on figuring out the antiderivative of cosine of t cubed. Good luck. I say that to all of us. It's going to be really, really difficult. Although you will learn a way this year on how you could do something with that. But not yet. Okay, so if you know the FTC2 concept, I think you should be done. Can anybody explain what you got to do? What's the idea here?
You plug in like the 2x cubed into t.
Where are you getting 2x cubed?
Oh wait, I'm on the wrong one. I'm sorry. But once you plug in, x squared into t and then find the derivative of x squared.
Yeah, that's exactly right. So, let's get the answer down here. So it'd be cosine of x squared cubed, and then the derivative of x squared, of course, is 2x. So that would really be your answer right there. But let's take a step back. I wanted to see if you knew what to do. Maybe more important than knowing what to do is why is this even FTC2? Like, why would you try to use the thing that Cameron just told us to use? What do you see, Jack?
Because it's the derivative of an integral.
It's not just the derivative of an integral, of a definite integral. And then what specifically about the definite integral tells you that it's FTC2? Say again?
Sorry, there's a variable.
There's a variable as
Limit.
one of the limits. Yeah, one of the limits is a variable. Obviously, that's the one right there. So if you've got the derivative of a definite integral, and the definite integral has one of the limits that's a variable, like you said, then that's a big indicator FTC2. So you want to watch out for that. If this right here was not a variable, if it was a constant, then the answer would simply be 0. Yeah, so if this was a constant instead of some variable, then you just get ddx of a constant, and the whole thing would just end up being 0. You can simplify this, of course, cosine of x to the 6th times 2x. There is no plus c here. Why is there no plus c? What's that? It's a definite integral. And not only that, if there were a plus c somehow still, the derivative, right? You'd be doing the derivative of that plus c, which is 0. Derivative of a constant term is 0. So two reasons why there's not a plus c. All right, number 3, a little more challenging. Definitely calculator active. It says if f of x equals that function, find the critical numbers of f of x on the interval from 0 to 2. So this traces back, kind of connecting back a little bit to chapter 3 in preparation for what we're going to do next. So if you would, please take a look at this, see if you can figure out the critical numbers, calculator being active, of f of x on 0 to 2. Okay, so then number 4. No, is there a number 4? I don't know. There's not. Oh, yes, the net change theorem. This is good. So basically, what we've done here in 4.4 is we have covered all of kind of the nitty-gritty detail stuff. From here on out, it's all application. This is where we get into some more interesting application type ideas. And so let's take a look here at this net change theorem. This is kind of the focus of the rest of section 4.4. So velocity. If you have the definite integral from a to b of a velocity, and I've given you units that are like miles per hour, do you guys remember what the definite integral of velocity is? 2 ways you could say again? Not quite. So I would say that the indefinite integral of a velocity function gives you a position function. This is a definite integral. There we go. A definite integral of velocity does give you displacement, and I am going to write it out a little bit differently as well. So displacement is totally correct. Wouldn't this give you, let's see, I'd say position at B minus position at A? Going back to kind of Brandon's idea of the indefinite integral of velocity does give you a position, but it's a definite integral. So displacement really is position at B minus position at A. Or you could just say that difference right there is really the change in position. Going back to the idea of the net change theorem, the net change theorem says the definite integral of a rate of change will give you the amount of change. It doesn't give you the amount, it doesn't give you the total amount, it gives you the amount of change. So for instance, if somebody said, hey, I changed my diet and I lost 20 pounds, does that mean that they weigh 20 pounds? No, probably not, unless they started off at 40, right? So when somebody says that their weight changed by a certain amount, in order to know what they actually weigh, wouldn't you have to know what they had at the start? That's the difference between knowing how much they weigh versus how much their weight changed. Same idea. Just because you do the definite integral of velocity and you get some number, that doesn't mean that is the actual position of that object or person or whatever. It just means that's how much their position changed. A leaky tank. Let's say that you've got gallons per second leaking out of a tank, and you do the definite integral from A to B. Well, the definite integral of rate of change gives the amount of change. So what would you say the definite integral of gallons per second dt would be? How would you describe that? Go ahead.
The gallons leaked, like the amount of gallons.
Okay, yeah, the amount of gallons leaked. You could say the amount of gallons that left the tank or leaked out of the tank. You could also just be generic and say it's the change in the number of gallons. Again, I'll say it. The definite integral of a rate of change gives the amount of change. So gallons per second is a rate of change. The definite integral of that will give you the change in the amount of gallons or change in the number of gallons. That's the general principle. The definite integral of a rate gives you the net amount of change. The net amount of change. Okay, so we'll start off with some really basic stuff, and we'll work our way towards some less basic stuff. So if you would take a look at example number 1. It says gasoline flows out of a storage tank at a rate of R of t, measured in gallons per hour. Find the amount of gasoline that flows out of the tank from t equals 2 to t equals 7 hours. Ready to go? Hopefully look like. I try to picture this as like number 11 on some quiz or number 22 on the AP test, right? Like out of context. So you look at this and it says, gasoline flows out of a storage tank at a rate of, and you'd look at this and be like, hey, that's a rate. So that's probably pretty important, measured in gallons per hour. Then it says find the amount. And hopefully what you do is you look at this and say, hey, they gave me a rate and they want to know the amount of change, the amount that flows out of the tank. This is the net change theorem. And so I need to do the definite integral from 2 to 7 of r of t dt. And in case you're not familiar, it is totally okay when you're writing down a step like this to write the name for the function versus the rule for the function. You do not have to write 5,000 minus 2t squared for your integrand. I mean, just write r of t if you want. So then at this point, you'd hopefully, have we done math 9 in here yet? I can't remember. Have we done math 9? Okay, so you do math 9 and you come up with what number? 667. And that would be measured in what? Gallons, yeah, because it is an amount gasoline. You guys have any questions? Okay, let's roll on then. So this next page has everything to do with the application to motion. And so here is, oh, come on. Here's the general concept. This is a term that somebody mentioned earlier, displacement. Displacement is the net change in location from starting point to ending point. Of course, you've heard this analogy before. I'm sure I've used it many times. This morning, hopefully you woke up in your bed, and hopefully later on tonight, after you're done with your day, you'll end up in the same spot. And so your displacement for the day should be 0. If everything goes according to plan, your displacement should be 0, right? If your displacement for the whole day is something other than 0, hopefully you're not sleeping in the park somewhere, right? Hopefully you're going back to wherever you live and it's happier than the alternative. That is not the same as the total distance traveled or the total amount that you traveled, simply because you're here. So you moved. You're not still in your bed, right? So your total distance will be something other than 0. So displacement is equal to the definite integral from a to b of v of t. Looking at this graphically, here's how you could think of this, and I think the graphic representation is particularly useful. If you got v of t and t, let's try to represent your day. You start off, bless you, presumably with a velocity of 0. You wake up, unless you sleep in motion.
I sleep around.
That is impressive because you get to get exercise and rest at the same time.
That's why I'm so skinny.
Very impressive. So then you leave your house, your distance from your house increases. You get to school. Let's just say when you're at school, you're just kind of at school, and so your velocity is essentially 0. But then at the end of the day, you get back in your car, somebody picks you up, whatever, and you head back to your house. You get to your house and you stop, right? So the idea here would be, unless you ran some errands in the meantime, that this area right here and this area right here would be the exact same area, but because one's above the t-axis, the other one's below, they would essentially cancel out as you do your integral, right? And you'd get a displacement of 0. That is very different from the total distance traveled. This is literally like the number of feet, number of miles, number of meters, whatever it is that you moved during the day. And so for this, the integrand, we absolute value it. What does absolute value do to a number? Doesn't necessarily make it positive. Makes it not negative, right? Because 0, right? Makes it non-negative. We all knew what you were saying, of course. It is all good. It's easy to say that. Please don't injure yourself. So then if we were to draw a graph of the absolute value of v of t, wouldn't it look just like that red graph except for the part on the right? So it would look just like this. You wake up, your velocity is 0, you go to school, still that. But then instead of this part being down here, that actually gets reflected up, whatever, and turned into a positive, right? Or non-negative, maybe at the end there, velocity goes back to 0. So now this area is the exact same as before. So is this, but now all those numbers that are being accumulated are positives, and so this would end up being something that is not negative for sure and not 0 either, based on the way the graph is. So you could say distance could never be negative. Distance could be 0. Displacement could be positive, negative, or 0. That is why your car has an odometer, not a displacement-ometer, right? Because if your car measured displacement on the little odometer thing, then how could you get your odometer to read 0? Go back to the factory, maybe? Yeah, drive back to the factory. Now, if it's a Honda, Toyota, it's going to be tougher. You have to put it on a boat or an airplane or something. But yeah, you just take it back there, it'd be 0. It's not a displacement-ometer, it's an odometer, measures the actual total distance traveled. So this will be a chance for you guys to practice using your calculator and just trying to solidify these two ideas. Look at example number 2. Given that velocity function, find the displacement on 1 to 5, find the total distance traveled on 1 to 5. Please write it down, use your calculator to calculate, and ready, set, go.
Exactly.
Everyone's in insurance school like,
The auto.
all right. Yeah, really.
How many accidents have there been on the Autobahn compared to I-45? Like twice.
I have no idea. I don't know those statistics.
I mean, I'm not pointing fingers, but
That could be a valid statistic or not. I don't know.
regardless, I'm right.
Okay. So this is the general concept, except I forgot the other half of my absolute value. There we go. Hey guys, listen up. Numbers wise, how'd this turn out? What about the displacement? So say again. 10.6 repeating essentially. Okay. Feet, right? And how about the total distance traveled? 11.883. Okay. 833. Okay, also in feet. So the fact that the total distance traveled and the displacement are two different numbers, what does that imply?
It's going backwards.
At some point, right? It turned around somewhere in there. That's why they're different. If they were the same number, then that means it never turned around, right? The displacement, total distance traveled would be the same. They never turned around. Just kept on going. Okay. Before we leave that, any questions? Okay. All right, so then we're going to do kind of a dry application of this, then we'll get into our more contextual applications. So we've already talked about Math 9, FN int, that whole routine. So example 3 is a place where this would be very useful. So this says find f of 5. It's telling you what to do. And it says if f of 1 equals 3, and f prime equals root log t. So root log t, kind of complicated. Sorry, this should be f prime of t. Sorry, let me fix that. F prime of t equals root log t. Shouldn't say f prime of x. So if I give you stuff about f prime, and maybe a little stuff about f, but I primarily give you stuff about f prime, but then I ask you, well, what's the value of f? What are you going to have to do in there somewhere? Have to do an integral. So maybe we say this. The definite integral, I'll say definite integral of f prime of t dt equals, and we'll fill in some details here. If I was going to do a definite integral, because I want to find this amount of change, what limits of integration would I have to put on the definite integral? Integral from where to where? 1 to 5, yeah. So here's why I'm going to pick the 1 and the 5. Of course, it is not arbitrary at all. I picked the 1. Why would I use the 1 as one of my limits? Yeah, we know about it, right? We were given f of 1 equals 3. We know everything we need to know about it. And then why would I make the other one 5? That's the one we want, right?
Do you add 3?
We'll get there in a second. So here is where I think FTC 1 and 2 really are illustrated nicely. What is the antiderivative of f prime? F. And then it's evaluated from 1 to 5. So what I could write here is this. I'll do this in one step, and if you don't like this, I can show you some other baby steps, and that might be helpful. That would be a big step. What do you think about that? The antiderivative from 1 to 5 of f prime is equal to f of 5 minus f of 1. Notice two things have happened. The antiderivative has undone the prime part of this, and we're finding the difference between the upper evaluation minus the lower evaluation. That make sense? Yeah? Okay. So then how does this work? How does the 3 come into play? Well, we know that f of 1 is 3, so I could rewrite this as f of 5 minus 3. And then I've got this expression on the left, not very pleasant, right? We know that it's integral from 1 to 5 of root log of t. And so this would be where math 9 would come into play. So what you would do essentially, once you have this set up nicely, you would math 9 the left side, and then just add 3 to both sides. Okay, so again, practice using your calculator with math 9. Make sure you are fully familiar and capable of doing that perfectly every time, and we should be good. So has anybody done this and then added 3 to both sides? You have a number? Alex, what'd you get?
I got 5.561.
5.561 equals f of 5. Okay, you guys, I'm seeing a lot of positive head nods there. Okay. Any questions? This is really the thing right here. I mean, the Math 9 is pretty easy once you figure out which buttons to push and all that stuff. It's the setting of it up that I think would be helpful. Brandon, question?
Oh, wait, never mind, sorry. I was thinking for some reason it said f of 5 plus f of 1 equals 3, but I'm just stupid.
No, you're not. That would not be the word I would use to describe you at all. You're just a human and you make mistakes. That's basically it.
That's true as well.
That's true of all of us. So, okay, so that right there, Jeff, that is the value of this.
Oh, yeah.
And so they get f of 5, we have to add the 3 over. Okay. We got about 5 minutes left. Let's see what we can do here with our final 5 minutes and our example here. Let's do a little bit of, we're going to do a little jumping around. Let's do this one. Let's do example 5. We're just going to do A in example 5. I think this is a real good one to finish with. So when I see you tomorrow, Lord willing, we'll just pick up with example 5, and we'll do the other 2 examples, and that'll be a good wrap on the whole thing. So here we go. So this will fit in, I think, pretty well with what we've been working on. This gives us this wonderful graph right here. It says the graph of f is shown above. Whenever I see that, I'm going to write equals f. And I'm going to write something else up above there as well here in just a second. But gives you this graph of f. Then it says let g be the function given by g of x equals, and this is where this is very different, right? We are used to seeing g of x equals sine of 2x. We're used to seeing g of x equals 5x squared plus 3, or e to the x, or ln of something, whatever. But this is a really kind of unique and kind of new way of looking at this. This is what we call an accumulation function. So we're basically saying that g of x is equal to the accumulation of area on f from -3 to wherever being the x. Does that make sense? So we call this an accumulation function. And then it goes on in A. We're just going to do A right here. It says find g of 0 and g prime of 0. So g of 0 means the exact thing you think it means. Just doesn't it mean plug in a 0 wherever you see an x? Doesn't mean plug in a 0 wherever you see a variable. It's specifically an x. So I could write g of 0 equals the integral from -3 to 0 of f of t dt. So then the question becomes, well, that's nice and everything, but how on earth am I supposed to figure out the integral from -3 to 0 of f of t? Because I don't even have a function for f of t. I use area. That's right. So if I use area, I'm going to basically calculate the area from -3 to 0. And as long as you can figure out the area of a trapezoid or a triangle and a rectangle, you're good to go. What is that area?
9 halves.
Yeah, 3 plus 1.5, which is 4.5. 9 halves, same thing. Now, the other piece to this is they also want us to find g of 0. And this is where the ordering matters. If you're going to find g prime of 0, let me ask you the ordering. Do you plug in a 0, then differentiate, or do you differentiate and then plug in a 0? Differentiate first. You do have to do it in that order. So here's where FTC2 sneaks its way in. If I want to find g prime of x, aren't I essentially differentiating both sides? So I'd say g prime equals the derivative of the right side. At this stage, I've basically just differentiated both sides. but I can simplify the right side because I know that the right side is really FTC2. So we could sing a song about it, agreed. I won't, you can. So if you use FTC2 to simplify that, what do you end up with on the right side? F of x, yeah, the x just drops right in there for the t, and the derivative and the antiderivative cancel each other out. You get g prime of x equals f of x. I would say that this, what I've written right here, is hugely important. You must connect those two. And by connecting, I mean you need to write them down. Write that down. So then g prime of 0 is what we're really trying to find. So I plug in a 0 for x. G prime of 0 equals f of 0. And if you look at the graph, it's a graph of f. And when x is 0, f is 1. You're right. And so you'd say g prime of 0 equals f of 0 equals 1. You could look at that and think that it's really simple, but it is not. If you understand that well, you understand a lot. You understand a lot about calculus and derivatives and integrals and all that stuff, area, values of functions, and that's obviously very good. Okay, that was almost perfect timing. You guys are good to go. Have a wonderful rest of your day, and I will see you. We'll finish this up tomorrow.